Hello, welcome to part 2 of our video where we're talking about setting up a RF amplifier model in AEDT Icepak. In the first part of this project, what we did was we defined our geometry. We built our RF amplifier box, which is shown in green here, which has some heat sources or devices right underneath the heat sink, which is colored red and attached on top of the amplifier to conduct the heat away. Also, our cooling mechanism involves a fan, which pushes air to convect the heat away from our amplifier. In this video, what we are going to do is first we're going to define some monitors where we want to track some flow and thermal parameters as the iterations go by to make sure we have convergence. We then are going to do some meshing operations. We want to have a good quality mesh near critical regions such as the heat sink and the fan to capture the flow and thermals adequately. And then we're going to submit our job, execute it, make sure the flow is converged, and then we're gonna look at the solutions to see where the hot spots are. If the solution makes sense, we're gonna look at the flow field, and we're gonna do that using AEDT Icepak post-processing capabilities. Since we have a fan which uses a fan curve, we necessarily are not specifying the mass flow rate, and therefore it's part of a solution. So I would like to see what the volumetric or the flow rate is across the air domain. So I'm gonna select my opening here, and what I would like to do is I want to assign a monitor on this face, and I would like to look at the mass flow rate. And I could also maybe look at the temperature. So let's hit OK. Another thing I want to track through iterations is the temperature. On a location, why don't we pick one of our sources? So if I select rectangle, one of our devices which acts as a heat source, I'm gonna assign a monitor to that face, and let's track maximum temperature, for example, and hit OK. So as you will notice under monitor, now we have two things. We can obviously rename these, but for sake of saving time, I'm not going to do that. Next step is meshing. Now in AEDT Icepak, let me quickly show you the meshing option. So we go under Icepak. If we click on simulation, we have essentially two different approaches, I would say. One is one can use the automated mesher, which most likely will work pretty good for this particular geometry because it's fairly simple shapes, nothing overly complex. And one could typically set a resolution. Usually I would suggest 4, maybe 5 levels. So as you move this slide bar to the right, it's going to have a finer and finer mesh with a larger mesh count. So that is definitely one option. So let's go ahead and set this to 4, hit OK, and then generate our mesh. Just see, you know, what the simplest method can provide us. Because we have a fairly simple geometry, you know, this possibly will work well. What you will notice is on the bottom right hand side under this progress window there was some activity, because meshing might take some time, and you know, users may be wondering what's going on. In this particular case, you know, we have very simple small geometry, so the meshing was very fast. Actually, you know, completed it. And then you know, we can see our in this window we can now look at our mesh display. So this show button will turn the mesh on or off, and right now it's showing on a cut plane. You can also look at the mesh on some boundaries. You can define different planes to look at the mesh. So, you know, let's for example now look at a mesh at a white plane, which kind of cuts through the center of the amplifier and the heatsink. And here you can kind of see, you know, how the meshing is done. And as you can see, it's decent, but you know, fairly coarse mesh. You probably want to do a better job resolving the flow, not just by maybe 4 elements in between, maybe go up to 10, 12 elements in between fins. We can use the slider, and then here again, you know, we can see the quality of the fan mesh, and as you can see, it's doing some multi-level meshing, cut cell methodology to capture the fan curvature. We have a total mesh count of around 94,000, which is fairly low. You know, for a problem like this, maybe you could easily go to at least 500,000 to 1 million and, you know, run it fairly quickly and then get a much better resolution for your flow and thermal field. But again, for preliminary analysis, this is a decent mesh. You know, you can just quickly look at the results, you know, by executing this. So why not, you know, let's give it a try. Another thing with the meshing, before we run it, you want to check the quality. So we have 3 criteria for this: face alignment, volume, and skewness. Typically, you want to be over 5% with face alignment, while we're over 60%, which is excellent. You don't want any negative values in this box here, which we don't. And when we look at skewness, again, this is about 7%. You want to be always roughly over 2%. But again, a lot of the cells, a big bulk of it is in excellent skewness. So that's great. We made our checks. Another thing before, you know, I like to do is click the validate button. This is like a final check and kind of says, hey, you know, okay, you got your settings, mesh, but you really haven't set the analysis up yet, which is correct. We have not. So let's go ahead and do that. So when we go back, here's our setup button. So we can either do it here, or another option is we can go to analysis and add a solution setup. So when we click here, it's going to bring up a new window, and we can do, you know, multiple solution setups. Maybe, you know, set up one case with radiation, one case without radiation, give them different names. So all the problem definition is done here. So here, let's, you know, just, we can just leave this, or maybe call this coarse mesh. Let's have a maximum number of iterations of 300. We want to solve both for temperature and flow. It's going to be a turbulent flow. let's look at our options. Well, it's fairly coarse mesh, and we really, just want to get a simple solution. We can just stay with the zero equation option. We don't want to deal with radiation at this time. We can add that later on if needed. Now, we do want to include gravity, because we have some air domain that is not forced convection within the RF amplifier. So I'm going to check include gravity here. And let's move left. So let's look at our convergence. These are default values, 3 orders of magnitude for flow, 7 for energy. We may just leave those as it is. Let's do some flow settings. We can just leave everything, all the velocities at 0, and temperature at ambient. And let's look at advanced options here. So if you ever run into convergence issues, this is where maybe you want to start making some changes to get a better converge solution. And I will not be talking much about this in this tutorial. So that's our setup. And one thing I'd like to note is, since we included gravity, we also have to define the direction of the gravity, in which direction it's acting. So next I want to do that, but let's hit OK for the time being and save our changes. So to add the gravity direction, I go under Icepak and design settings. I kind of really don't like this. This is either the naming, or there are some critical information here which sometimes need to be changed, and it's kind of hidden under the design settings name, which I'm not very comfortable with it. I wish Ansys changed this, but here you can define your ambient conditions, which we'll use as 20 degrees Celsius. Now here we want to do our gravity, and looking at this, the gravity should, if we assume it's sitting on the YZ direction, it should be in the global X and should be in the negative direction. And let's see what else is hidden here. Looks like that the rest are kind of really some options that are advanced. If you want to include altitude effects, or if you want to use ideal gas flow or operating density. So let's hit OK and get out of this. I believe we have the setup completed. So it's now under here. And then looks like it's time to execute our model. Let me show you one more thing here. I have a 24 core machine. So here, here you can change your number of tasks and cores. 12 cores may be overkill for this, but let's just stick with it. So, and then next step is you can do analysis, analyze all, or again you can click this button directly here. Let's click analyze all, and let's start concentrating on the bottom right hand side and see if there are any problems. Here what I'm noticing is my Minex object does not have mesh, stationary wall does not have mesh. So this seems like a serious warning. Let's see, this probably means we'll have to remesh our model. These walls are pretty thin, and I believe probably they kind of got walked over. But let's see, I mean, if it still runs, do the results make sense? So right now what's happening is it wrote out a model for Ansys Fluent. As you know, in the background Ansys Fluent is being used as the solver, and what we're seeing is iterations going through. fluent. Another way to track this is, so if we go to the results tab, we can look at solution data. So when we click this, it tells, you know, kind of the status, it's still ongoing. If we click residual tab, we will see how our residuals are behaving. They're behaving very nicely. Things are, you know, going down steadily. Remember, we added some thermal monitors. So what we're seeing is some really extreme temperature for the heat source, which does not seem realistic, which kind of tells me, you know, that there's a problem in the model. So, you know, even without waiting for a solution, we can see there's a possible problem. Let's look at the flow monitor, and looks like, you know, this is what the flow field is doing. Maybe just too little mass flow rate through the system. So these are the early indications of, you know, a clearly poor solution. You know, so even though convergence is good, it looks like the solution does not make sense. You know, to fix this, typically, you know, when you have a problem, a lot of times it's in the meshing, it's in the setup. And in this case, you know, we have some indicators here, some warnings in our log window at the center bottom. So let's heed these warnings, do a remesh, and recalculate our solution. So let's go back to our simulation button. Let's go to global mesh settings, and let's start using some advanced options. So I'm now going to use the switch to user specified mesh controls. I want to put a maximum mesh size of maybe 5 millimeters here, because the X direction, there's a lot of variation, so we want to keep that small. And then 30 millimeters in the Y, maybe 15 millimeters Z. And let's just have minimum gap of 1 millimeter, that's fine. I don't want to use multi-level meshing, and I want to keep these mesh parameters the same. Let's hit OK. And let's generate our mesh, see how that works. Now we have, again, you know, the mesh count did not go up by much. So let's click show, start looking at our mesh, but it seems to be, you know, finer. So maybe it's doing a more advanced way of meshing. Let's kind of move to a center plane. And as you can see now, you know, we have many more cells in between. Instead of 4, we have about 8 to 10 cells in between. And we can go finer than this, but this is just a demonstration, so I want to stay here. Let's look at the quality. Again, skewness is good, face alignment is good. We have some still the warnings here. So this Minex object does not, and stationary wall 1. So this essentially, you know, has to do with our thin wall here, because its thickness is we had defined this as a surface on the back side. So this could be a problem. Maybe we do want to change this type of a boundary condition. So here what we notice is the thickness of this element is just 1 millimeter. So if we go back to our mesh settings, we'll notice that we're essentially, maybe a little too large maximum element size, so it's getting overwritten. So let's see, let's try a 2 millimeter maximum element size and hit OK, and let's generate our mesh again. So this could add quite a bit to the mesh count. So it kind of doubled our mesh, but it's still reasonable. So let's see. Now, looks like, that problem is gone. So that's good. We didn't have to change the setting. It was just we needed a bit more resolution there. So let's show our plane mesh, and as you can see now that bottom thickness is resolved, so it's captured in a cell and we do not have any issues. Let's quickly check our quality, face alignment 50%, very good, skewness 30. So that's also very nice. So now let's resubmit our job. So I'll click Analyze All, and let's send it to the solver. So once the solution is converged, I want to look at the solution data. I want to first look at the residuals, see that, it's pretty good. Maybe, converge it a bit better. Seems like things are still going down. Thermal monitor, we have reasonable results. It's, getting pretty hot. This is just the maximum, not the average, but that seems reasonable. The air temperature is rising, the iteration. So it might be a good idea to add some more iterations. Flow-wise, it has settled. We are seeing a reasonable mass flow rate expected from the fan. One thing I want to mention is when I ran the model, I noticed that my maximum temperature was very high for our devices. So that means two things. Either the flow rate is low or the heat source is too high. So what I did was I went back to my source and I made a correction here. I changed the total power to 7. This I had previously said it was 84, where it was a mistake. Because this source contains multiple objects in it. So the power value is per object, not the total power. So you need to be careful with that. I made that mistake of, because we have 12 objects, I multiplied 7 by 12 and put 84 here. But then it actually, what Icepak does is use 84 watts per each of these 12 heat sources. So you still want to put a total power of per heat source. So please be careful with that. So once I made that fix, the results did make sense. So let's see, we talked about solution data, talked about convergence. Now let's do some post-processing. So one of the things maybe we want to look at is using field summary, some temperatures, some values, some averages. For example, let's look at the temperature field for our sources. So we're going to look at source 1. We can select or restrict our entities here, and we can pick sides as well. But so for source 1, I want to look at temperatures, and I want to add this as a single calculation, for example. So when we look at it, we see the minimum, the maximum, and the mean value for for our sources. We can look at all these different things. For example, let's look at our velocity. So maybe, in our opening, which is our outlet, let's look at the flow speed. Let's add this as a single calculation. So it's going to add a new row here. And as you can see, we have a maximum of 6 meters per second of flow, which is very reasonable for a fan. And then, there's some lower flow regions, of course, with an average of around, over 1 meters per second. So that's good. And again, we can look at maybe something like a heat flow. What if we picked, let's see, what if we pick an object? We look at our heatsink objects and let's see how much heat flux goes through these objects. I'm gonna just add them as a single calculation. So let's add these as a single calculation, so it will be one value for each, a combined value for all of these components. And what we'll see is, how much heat is passing through this system. Or, maybe we can add as multiple calculations. So now we can see what each individual component does in terms of heat flux. So this tool can be used, very effectively to get in numerical information. Now, I'm going to talk about some visual post-processing. So one thing we can do, maybe let's take a look at on our heatsink what the temperature profile does look like. So here, what I'm going to do is I'm going to my heatsink object, go under solids. I'm going to select all my surface, all my solids. I'm going to say plot fields, temperature. Let's see, and select temperature. So this could be maybe temperature 1. And I would like to just see it on the surface, not volumetric. So I want to tick this box and click done. So now it does a post-processing, and as you can see on the screen, it's going to show us our temperature profile, which, when I look at it, makes a lot of sense. So what's happening is we have these hot spots at our heat generating devices. So it's hotter there. As you can see, it is cooler near where the fan is effective. And as we move away from the fan, and as the then, with addition of heat, things are getting hotter in the y direction as it goes downstream, and we have the peak temperatures near those regions, and then that heat essentially is conducted away through the heat sink, and the convection essentially takes the heat away from the heat sink itself. So we can make a lot of decisions looking at these results. Maybe one could add more fins in this region, maybe use a stronger fan if temperatures are too high in certain regions. Another way to look at the solution is making a plane cut and looking at maybe temperatures, velocities on that plane. So then, you could see air related properties better, because right now, we're looking at solids and surface temperatures. So let's do some section cuts. The way to do that is a little inconvenient. It is under Icepak, under Toolkit. You want to go to Reporting and Cut Plane. So this is essentially a special macro or a tool that is taken from classic Icepak, where you can define a section cut, and you can select, you know, vectors or contours on that section cut. So maybe, you know, I'll just call this Y plane. We don't have to name it. We can have it go through Y plane through center. We can look at contours or vectors. So let's start looking at some contours. I want to look at temperature. So what I'm going to do is click Create and kind of move it away. So what we now see is, well, let's hit Exit, is the temperature field right in that center, and that gives us very good detail. So what are we seeing here? This is the air cavity inside our amplifier. Remember, we had some backside cooling on this bottom wall. So you see the cooling impact there. You see the hot region that corresponds, you know, to the region where these devices are providing heat. So you have your hot spots in these three locations, and then you can clearly see the hot heatsink profile and the cooler air that goes through the fins. So this is an excellent way to visualize the thermal field, what's happening through our amplifier and our heatsink. As you'll notice, as I create these post-processing, we're getting these objects under field overlays. The first is that temperature, you know, and when I click on it, it's going to highlight the surface temperature on the heatsink, and then that white plane that we created. I'm just going to give one more example for post-processing, and then I think I'll wrap this tutorial or demonstration up. So again, let's go to our Icepak, Toolkit, Reporting, Cut Plane. And as you can tell, this is one of my favorite features. I want to do, let's look at an X plane. And I now want to show vectors. And I'll just say Create. And looks like it's not very happy. Okay, let's click Continue. So maybe let's hit New. Okay, so I think that worked better. And exit, and let's see. Oh, I do not see an overlay. So, but I do. So let me hide this one. Let's hide this one. So the last thing I want to show is maybe quickly generate another contour plot. As you can tell, I like contour plots. I want to do and explain through the center. I'm going to look at contours, but this time I want to look at the velocity contours. Let's hit OK. Let's say Create. So it's going to work. Load in the data, and then we can kind of see, you know, the velocities flow coming here fast, kind of slow recirculation zones. This plane cuts through the amplifier, so there's slow speed here. Maybe I do want to look at a section in between the fins. So let's see if I can move to a higher plane. Let's do reset. Now let's see if that worked. Okay, let's do another create. Now see our plane is cutting through. Center, let's look at not temperature, but velocity. Even let's look at the Y component this time. Let's just say create. And now we can see how the flow is distributed for the heatsink. And what you see is there's pretty strong cooling right in the center, but relatively speaking, much less cooling toward the side. So this design obviously could be improved. And this does conclude my presentation for today. Thank you for your interest. Have a great day.